3I Atlas. What if the worst-case scenario actually happened? What if this interstellar object, which does not belong to our solar system and travels at a speed never seen in common bodies, altered everything we believe to be under control? It is not a typical comet nor a traditional asteroid. It is a visitor from deep space, a fragment that comes from another star and whose exact nature is not yet fully understood. Telescopes detected it with a hyperbolic orbit, confirming that it is not bound to the Sun and that after crossing the solar system it will continue its journey into the interstellar void. But what unsettles scientists is not its shape, but its origin and trajectory. Objects like this do not follow known patterns. They do not revolve around the Sun like planets, nor do they return like periodic comets. They are unpredictable, fast, and difficult to study. And here arises the question that almost no one dares to ask aloud. What would happen if everything went wrong? If an unforeseen gravitational interaction with Jupiter altered its trajectory, if fragments broke off near the Sun, if part of that material ended up approaching Earth? This is not a prediction, nor a catastrophic warning. It is simply analyzing what physics would allow. Although the probability is extremely low, today we are not going to imagine fantasy. We are going to explore a what-if based on science, without lies and without alarmism. Before analyzing that extreme scenario, something must be made clear. 3 Atlas is not a confirmed threat nor an apocalyptic comet hidden by space agencies. It is the third interstellar object ever detected, after Oumuamua and 2I Borisov. Its mere existence is already historic because it comes from another stellar system and brings with it information about places in the universe we will never be able to visit. Current data show that its trajectory does not intersect with Earth. There is no risk of impact nor signs that it is deviating, but studying it is key because these objects do not follow known rules. What we will do here is not sow fear, but understand how science would act if, hypothetically, the course of events changed. Before we delve into the scientific analysis of a hypothetical worst-case scenario with the interstellar object 3I Atlas and humanity's planetary defense preparedness, you need to do 3 things immediately to activate the scientific community. First, give this video a like to bring this crucial analysis to more observers. Second, subscribe and turn on the bell to receive the next updates on the real-time tracking. And third, go down to the comments right now and write, "Preparation," to join the global registry of those following this historic event. Do it now. This analysis is not fiction. We are not going to invent that NASA is hiding information or that the world is going to end. We are going to use astronomy, orbital dynamics, and real examples from the planet's history to understand. If the improbable happened, how prepared are we? 3I Atlas is not just another object in space. It is a cosmic rarity. Its official designation begins with 3I, where the letter I stands for interstellar, meaning it was not born in our solar system. Before it, only 2 similar visitors had been observed. Oumuamua, discovered in 2017, and 2I Borisov, registered in 2019. That makes 3 Atlas the third visitor from another star that has been identified by humanity. Its study is crucial not because it represents a danger, but because it offers us a window into regions of the universe we will never be able to explore with conventional probes or telescopes. It was detected by the Atlas system, the Asteroid Terrestrial Impact Last Alert System, a set of automated telescopes that search for near-Earth objects. Upon analyzing its coordinates and speed, astronomers noticed something unusual. Its trajectory was not elliptical like that of planets, nor parabolic like that of some comets. It was hyperbolic. This means its speed is greater than that needed to escape the Sun's gravitational field. In astronomical terms, that confirms it is not trapped by our star. It is simply passing through. Its speed exceeds 60 kilometers per second, much greater than that of typical asteroids in the main belt between Mars and Jupiter. But the most perplexing thing is that its exact composition is still unclear. Some telescopes have reported slight activity around the object, which could be interpreted as sublimation of volatile materials, similar to a comet. However, other analyses indicate the absence of an obvious coma or defined tail, so its nature might be more similar to a rocky or fragmented body. Unlike 2I Borisov, which clearly exhibited cometary activity, 3I Atlas appears to be less active or perhaps is composed of materials that do not react easily to solar radiation. This reinforces the idea that we cannot categorize it with total certainty as a comet or asteroid. It remains simply an interstellar object. To understand its importance, one must remember that interstellar objects do not form here. They were probably expelled from their original planetary systems during early stages of planetary formation. Gravitational interactions with giant planets, binary stars, or even collisions could have launched these fragments into the interstellar void. Over millions or even billions of years, these bodies wander without a fixed course until by chance and gravity they approach our solar system. Detecting them is extremely difficult because they are small, dark, and fast. That is why each one represents a unique opportunity to study material that originated in another stellar system. The calculated orbit for 3I Atlas shows that it entered the solar system from a direction near the constellation Draco, and after circling the Sun it heads towards the constellation Virgo. It is not expected to ever return. Its closest point to the Sun, known as perihelion, has already been determined and does not bring it dangerously close to the inner planets. Earth is not in its trajectory. However, studying this type of object allows us to prepare for future visitors that could represent a risk. Planetary defense is not based solely on detecting immediate threats, but also on understanding everything that enters and leaves the solar environment. The behavior of 3 Atlas has been compared to that of Oumuamua, because both share certain anomalies in their movement. In the case of Oumuamua, a non-gravitational acceleration was observed that some studies explained as a result of outgassing, while others proposed alternative models. With 3I Atlas, any small change in its trajectory is studied to determine if non-gravitational forces, such as solar radiation pressure or the release of gases, influence its path. These measurements are fundamental because even small variations can reveal the object's internal structure, its density, or its possible irregular rotation. Understanding its speed and composition also allows for modeling hypothetical scenarios. While its trajectory does not represent a threat, astronomers use data like these to simulate what would happen if a similar object were deflected by gravitational effects. Jupiter, for example, has such an extensive gravitational influence that it can significantly alter the path of approaching bodies. In fact, many comets in the solar system have been captured, deflected, or expelled by this giant planet throughout the history of the solar system. Although 3I Atlas is not heading towards Jupiter in a dangerous way, studying how these bodies interact in simulations helps us understand how fragile the stability of an orbit can be. Studying interstellar objects is not just a matter of security, but also an incomparable scientific opportunity. Analyzing the light they reflect allows us to obtain information about their chemical composition. If they contain organic molecules, unknown minerals, or distinct proportions of carbon, silicon, or metals, that could reveal how planetary systems outside our own formed. These objects could even contain clues about how matter is distributed in the galaxy. The scientific community observes 3 Atlas not with fear, but with fascination. Every day its coordinates, its brightness, and its acceleration are updated to confirm that its trajectory remains safe, and so far it is. However, its study opens the door to an inevitable question. How ready are we if one day a similar object took a different course? To understand how science assesses real risks and discards rumors, it is necessary to understand precisely what we know so far about the trajectory of 3I Atlas. Observatories have collected enough measurements to calculate its orbit with a high level of confidence using mathematical methods based on celestial mechanics. Its movement is not random. It responds to the laws of Kepler and Newton like any other body, but with a hyperbolic trajectory that indicates it was never part of the solar system and will never return. This trajectory takes it to pass relatively close to the Sun, but not enough to disintegrate completely or be captured by its gravity. Humanity has observed thousands of comets and asteroids that follow elliptical paths and return in specific periods. But 3I Atlas has no scheduled return. Its speed exceeds the solar escape velocity, meaning that after its closest approach it will continue its journey into interstellar space without ever crossing our cosmic neighborhood again. So, why do we imagine an extreme scenario if the data says there is no danger? Precisely because science does not only observe what happens, but also asks what could happen under different conditions. This is not alarmism, it is prevention. When astronomers create hypothetical models, they are not predicting catastrophes, but studying the planet's response to unlikely but possible eventualities. This is how planetary defense projects like NASA's DART mission arose, which in 2022 managed to alter the course of an asteroid for the first time in human history. It was a successful experiment, not because the asteroid represented a danger, but because science anticipated a possible future. To visualize the worst-case scenario from a strictly scientific point of view, one must first understand what kind of physical conditions would need to be met for an interstellar object like 3 Atlas to impact Earth or generate severe consequences. The first possibility, although extremely improbable according to current data, would be a significant gravitational alteration. If 3 Atlas passed near Jupiter or Saturn at the precise angle, its trajectory could be modified. This kind of interaction is known as gravitational assistance or partial capture. However, current calculations show that 3I Atlas does not pass close enough to these planets to produce such an effect. The estimated minimum distance relative to Jupiter is so large that its influence would be minimal. Still, this type of scenario is studied not because it will happen, but because it helps improve the precision of orbital models and perfect early warning systems. Another scientific possibility analyzed in simulations is fragmentation near the Sun. Some objects, when they get close enough, fracture due to the combination of extreme heat, pressure from solar radiation, and gravitational tidal forces. This is what happened with comet Ison in 2013, which disintegrated upon approaching too close to the Sun. In a case like that, if an interstellar object fragmented and parts of its material became trapped by the Sun, new trajectories could be generated for those fragments. Some might fall back into deep space, others might end up in elliptical orbits, and a few, if they coincided with Earth's position, could represent a risk. The probability is extremely low, but it is a valid astrophysics exercise to understand the limits of our predictive capacity. In the practical case of 3I Atlas, no significant disintegration has been observed. It does not present a wide coma nor a massive shedding of material, which indicates it could be a rocky body or be coated with material that does not sublimate easily. If it were an object similar to Oumuamua with a hardened surface protecting its interior, its structure would be more resistant to solar radiation. What is monitored with caution is any change in its brightness or its light curve. Small variations could indicate irregular rotation or mass loss, which would add data for future models. Thinking about the worst-case scenario involves analyzing what would happen if, against all odds, a minimal deviation placed one of these fragments on a course towards Earth. To estimate potential damage, scientists turn to real examples of impacts or atmospheric explosions. One of the most studied is the Tunguska event in 1908 in Siberia, where an object of about 50 to 60 meters exploded in the atmosphere, generating a shock wave that flattened over 2,000 square kilometers of forest. No crater remained because the object never touched the ground, but the energy released was equivalent to between 10 and 15 megatons of TNT. If a fragment of 3I Atlas with an unknown composition and unforeseen trajectory impacted in a similar way, the effects would be comparable: localized destruction, forest fires, and a shock wave. However, to cause global damage, a much larger object would be needed, like the one that impacted the Yucatan Peninsula 66 million years ago, known as the Chicxulub event. That body measured between 10 and 15 kilometers in diameter and released enough energy to provoke global climate changes. So far, there is no evidence that 3I Atlas has dimensions of that type. The most accepted estimates suggest its size could be between a few hundred meters and a few kilometers, depending on its reflectivity or albedo. This data is obtained by measuring how much light it reflects and comparing it with known density models. That calculation is not exact, but it allows for an approximate idea. The important thing is to understand that science does not work with fear, but with probabilities. The more data collected about an object, the more precise its orbital prediction becomes. And with 3 Atlas, the current data are sufficient to affirm that there is no risk of impact. But this type of hypothetical analysis allows for the improvement of detection technology, the strengthening of planetary defense protocols, and the preparation of the population with verified information instead of leaving room for rumors or disinformation. The possibility of an interstellar object like 3I Atlas representing a threat depends on 3 essential scientific factors: its mass, its trajectory, and its interaction with other bodies within the solar system. So far, the data indicate that none of these variables points to a risk for Earth. But to understand why scientists study extreme, though improbable, scenarios, it is necessary to understand how these cosmic visitors are detected, tracked, and analyzed. When an object like 3 Atlas is detected, the first data obtained are its position in the sky and its apparent brightness. From several observations at different times, its angular velocity is calculated, that is, how fast it moves relative to the stellar background. If that movement is too fast to be explained by an elliptical orbit around the Sun, astronomers begin to suspect it may be an interstellar object. Then, using mathematical models based on universal gravitation, its orbital curve is calculated. If the orbital parameter known as eccentricity exceeds the value of 1, it is confirmed that it is following a hyperbolic orbit, meaning it is not bound to the Sun. That was exactly the process that allowed it to be officially classified as 3I. Once its interstellar nature is determined, The next step is to predict its exact route as it approaches the Sun and traverses the inner solar system. Although these calculations are precise, they are not perfect. Every object in space is subject to additional forces besides gravity. Solar radiation pressure, the solar wind, gas emissions if it contains volatile materials, and small irregularities in its shape and rotation can slightly alter its trajectory. These effects are minimal, but become relevant when trying to project its position years into the future. That is why constant adjustments are made as new observations refine the data. It is important to emphasize that 3I Atlas was not discovered because it represented a danger. No alert system was activated due to a threat. It was identified because its trajectory caught the attention of astronomers who monitor the sky for any unusual object. Its study does not respond to fear but to scientific curiosity. Knowing where it comes from, what materials it contains, and how an object that was not born under the Sun's influence behaves is fundamental to also understanding the formation of other planetary systems in the galaxy. Every measurement of its brightness, every image captured by telescopes in Hawaii, Chile, or the Canary Islands adds a piece to a much larger puzzle. How do planetary systems beyond our own form and evolve? However, science also analyzes the improbable. Although the current trajectory of 3I Atlas is safe, computational simulations are performed to estimate what would have happened if it had passed a few million kilometers closer to Jupiter or Saturn. The gravitational influence of those giant planets is so powerful that it has captured comets, altered asteroid trajectories, and in some cases, launched objects into interstellar space. Jupiter, for example, has been responsible for expelling thousands of small bodies out of the solar system. Its mass, equivalent to more than 300 Earths, makes it the planet's primary natural shield. If 3I Atlas had passed closer to it, although still unlikely, its trajectory could have been modified enough to bring it closer to Earth or even trap it temporarily in a secondary orbit. But none of that has occurred because the real distances between the two bodies are too great to produce a significant change. Another key aspect for studying extreme scenarios is the relative position of Earth. When these objects cross Earth's orbit, the fact that an object crosses the planet's orbital path does not mean it will impact it. For a collision to occur, the two bodies would have to meet at the same point in the orbit at exactly the same time, which is extremely improbable. In the case of 3I Atlas, its passage through the region where Earth orbits occurred weeks or months before or after our planet was there. For that reason, even though it crosses Earth's orbital plane, it does not represent a danger. This analysis is part of what is known as impact risk determination and is calculated with mathematical tools known as MOID, minimum orbit intersection distance. If we speak of the worst scientifically possible scenario, we would have to imagine a sudden alteration in one of these variables: mass, trajectory, or gravitational interaction. For example, if 3I Atlas had been much more massive than estimated, several kilometers in size, its own gravity would slightly affect its path, making predictions more difficult. But current photometric analyses rule out that possibility. Another scenario would be that upon approaching the Sun it fragmented violently and some fragments ended up on routes coinciding with Earth. Even then, the probability would be low, and current astronomical monitoring would detect any considerable change with enough advance notice to activate urgent observation protocols. There is no silent or sudden risk. The importance of studying these scenarios is not to generate fear, but to develop applied science. This is how NASA's Planetary Defense Coordination Office and the Center for Near-Earth Object Studies were born. To observe, calculate, and anticipate is what prevents a future eventual threat from taking humanity by surprise. It is not about imagining that 3I Atlas will destroy the world, but about using its passage to learn and prepare for any object that in the future could represent a real risk. Although 3I Atlas does not represent a threat, its existence forces us to analyze one of the least discussed but most important aspects of the study of cosmic objects. How much do we really know about planetary defense? And how prepared is humanity for an extreme scenario, even if it is unlikely? Modern science is not based on waiting for something to happen. It is based on anticipating it. Therefore, every time a foreign body enters the solar system, even if it represents an almost negligible risk, it becomes an opportunity to improve models, technologies, and protocols. Planetary defense does not consist solely of launching rockets to destroy space rocks. Before thinking about physically intervening, one needs to know precisely what is being faced. That means measuring its size, mass, density, composition, rotation, speed, and trajectory. Terrestrial and space telescopes take care of this. Through spectroscopy, scientists analyze the light reflected by the object to determine which chemical elements are present on its surface. If 3 Atlas reflects a certain amount of infrared light, for example, it could indicate the presence of minerals rich in silicon or carbon. If it emits certain patterns of ultraviolet light, it could be covered in ice or organic compounds. Every piece of data allows for the construction of more precise models. When it comes to real dangers, time is the most important variable. If a large object is detected with decades or centuries of anticipation, it is possible to alter its trajectory with minimal interventions. But if it is detected late, even if it is small, the margin for action is drastically reduced. That was one of the reasons why NASA launched the DART mission in 2021. The probe impacted the asteroid Dimorphos in September 2022 to test if it was possible to modify its orbit through a controlled collision. The results showed that yes, although the deflection was minimal. That experience demonstrated that humanity has the technical capacity to change the course of a small body if it acts with sufficient time. However, there is a critical difference between a common asteroid and an interstellar object like 3I Atlas. An asteroid that belongs to the solar system follows relatively predictable trajectories. It can be tracked for years or decades before it approaches Earth. An interstellar object, in contrast, appears suddenly, travels at much higher speeds, and does not return. That means there is less time to study it and fewer opportunities for intervention. In the case of Oumuamua, for example, when it was detected it was already moving away from the Sun. In the case of 2I Borisov, it could be observed in more detail, but it was also available for a limited time. 3I Atlas follows that same pattern. It is studied as it passes, but it will soon disappear forever. That is the main challenge science faces with this type of visitor. Let us imagine, based solely on science, how the worst possible scenario would function. Not from fantasy but from physics. For 3 Atlas or an object with similar characteristics to become a real danger to Earth, its trajectory would have to be modified by an unexpected gravitational interaction or by fragmentation at a critical orbital position. If, for example, during its passage through perihelion the object fractured and a part of its debris became trapped in an elliptical orbit around the Sun, it would be necessary to calculate if that new orbit would intersect with Earth's in the future. The probability is extremely low, but that is the type of analysis astronomers perform. It is not about guessing the future but about modeling all possible futures that the laws of physics allow. If any of those fragments, no matter how small, were headed towards our planet, space agencies would activate established protocols. The European Space Agency's Near-Earth Object Coordination Center and NASA's Planetary Defense Office have tracking and alert systems. The point and date of possible impact would be calculated. Then, scenarios for evacuation, mitigation, or intervention would be developed. If the object were sufficiently large and there were enough time, sending a deflection mission could be considered. If time were insufficient or the object were small, strategies for local or regional evacuation would be prepared, similar to those used for hurricanes or earthquakes, but with greater anticipation. An example that helps to dimension this is the Chelyabinsk event in 2013. An asteroid approximately 20 meters in size entered the atmosphere over Russia and exploded at an altitude of about 30 kilometers. The shock wave broke thousands of windows and caused injuries to more than 1,000 people. No one died, but it was a warning. A relatively small object, not detected in time, can cause damage. Now, if it were larger, around 100 to 200 meters, the impact would be much greater. Therefore, the study of 3I Atlas serves to perfect early detection techniques, even if it is not dangerous. Observing it improves the systems to detect others that could be. When speaking of the worst-case scenario, science does not imagine it as an inevitable extinction, but as a chain of events that can be studied, calculated, and in many cases avoided. 3I Atlas does not have sufficient mass to alter Earth's orbit, nor a trajectory that crosses our planet, but it represents an opportunity to remember that the universe does not revolve around us. We are part of a dynamic system surrounded by bodies traveling at enormous speeds, under precise physical laws, but not always predictable if observed too late. Therefore, to study, prepare, and communicate responsibly is the only way to face the improbable with intelligence. If one wants to understand how humanity would truly react to the worst possible scenario with an object like 3 Atlas, it is necessary to observe how it currently does so when facing real or at least potential threats. It is not just about telescopes pointing at the sky, but about an international system of surveillance, simulations, scientific protocols, and cooperation between space agencies. This ensures that even if an object represents a minimally elevated probability of impact, there is no improvisation, but rather a response based on data and previously established procedures. Science in this sense does not act when the danger arrives, but before it even exists. Although 3I Atlas does not represent a danger, its passage is useful for testing this silent infrastructure. Observatories on different continents record its position and transmit the data to centers like the Minor Planet Center, which centralizes the information and updates orbital parameters. These data are used by NASA, the European Space Agency, the Japanese Aerospace Exploration Agency, and other institutions to compare their calculations. Every minimal change in the trajectory is incorporated to refine the precision. This guarantees that if something unforeseen arose, the systems would detect it with anticipation. But what would happen if, in a scientifically rigorous hypothetical scenario, the data began to show that one of the fragments of 3I Atlas, as a result of a breakup or orbital alteration, had a probability distinct from zero of approaching Earth in the future? The first thing would not be panic but analysis. Scientists would apply Monte Carlo algorithms to study millions of the object's possible trajectories, considering uncertainties, potential measurement errors, non-gravitational forces, and perturbations from nearby planets. In this way, what is known as the orbital uncertainty cone is obtained, which indicates in which regions of space the object could be found in the future. If any of those regions coincided with Earth, it would be classified as a potential risk. At that moment, the information would pass to systems like NASA's Sentry or the University of Pisa's NEODS, which automatically analyze impact risks. If it were within concerning parameters, an international notification would be activated. However, it would not be announced as an inevitable catastrophe. The data would be exhaustively reviewed because often, upon obtaining new observations, the probability of impact is reduced to zero. This has happened with several asteroids. For example, the asteroid Apophis was considered for a time as a possible risk for the year 2029 or 2036, but new observations completely ruled out that possibility. That is how science works. First it detects, then it refines, and finally it concludes. Now let us imagine that the probability does not disappear entirely. In that case, governments would be informed through the International Asteroid Warning Network and the Space Mission Planning Advisory Group. Options for deflection would be discussed if the object were large, or plans for local evacuation if the object were smaller. This is where active planetary defense comes in. Different proposed methods exist, some already tested, others in development. One consists of directly impacting the object to modify its trajectory as DART did, but on a larger scale. Another proposes placing a spacecraft near the object, using its gravity as a kind of gravitational tractor to slowly alter its movement. Alternatives are also studied, such as concentrating solar radiation with space mirrors to evaporate material from its surface and generate thrust. Extreme options like nuclear explosions in space are considered only as a last resort and not to destroy, but to fragment or deflect. Even if none of this were possible due to lack of time, prior knowledge would still be useful. It would allow for the determination of the entry point into the atmosphere, the possible impact location, and the energy released. With that, regions could be evacuated, infrastructure reinforced, or the population warned. The key is not to avoid something hitting Earth at all costs, but to prevent it from doing so by surprise. History demonstrates why this matters. When the Tunguska event occurred in 1908, no one expected it nor understood it. If it happened today, satellites would detect its entry, its trajectory would be calculated, and authorities could act. That is the current progress of science. 3I Atlas serves as a reminder that we are not isolated from the universe. Earth moves at nearly 30 kilometers per second around the Sun, while hundreds of thousands of rocks, fragments, and icy bodies cross nearby paths. Life on this planet is possible thanks to extraordinary conditions. The exact distance to the Sun, the presence of an atmosphere that protects from radiation, a magnetic field that deflects solar particles, and a moon that stabilizes Earth's tilt. That stability has allowed life to persist for millions of years, but it has also been interrupted, as demonstrated by the Chicxulub impact 66 million years ago. That event did not mean the end of life, but the end of the dominance of certain species. Earth recovered, but it was not the same. Today, unlike millions of years ago, technology, science, and response capacity exist. The goal is not to live in fear of every object that crosses the sky, but to understand that the universe is dynamic and that the responsibility to protect life also belongs to those who observe, calculate, educate, and prepare. 3I Atlas does not threaten our world, but it forces us to look beyond the immediate, to recognize that knowledge is the best defense against the unknown. The question many people ask, even when science has already ruled out a real danger, is whether an object like 3I Atlas could affect the Sun or trigger a dangerous solar phenomenon. This question appears frequently on social media and in sensationalist media, but scientifically it is important to clarify what is possible and what is not. The Sun is a star with a mass 333,000 times greater than that of Earth, and its gravity completely dominates the solar system. Every planet, asteroid, and interstellar object that approaches falls under its influence, but its mass is so large that an object like 3I Atlas, even if it measured several kilometers, would not have sufficient force to alter its behavior. The Sun daily faces impacts from much more massive material, like Kreutz-type comets, which disintegrate on its surface or in the solar corona. And yet, its activity continues normally. What can happen, and has been observed, is that an object approaching too close to the Sun fragments due to tidal forces or vaporizes due to the extreme heat. These events are called sungrazers, comets that graze the Sun and usually disintegrate before impacting directly. The released material disperses and is absorbed without causing visible large-scale alterations. For that reason, when analyzing the worst possible scenario from a physics perspective, it is done with respect to Earth, not the Sun. The Sun is too massive to be affected by small bodies. Hence, scientific attention focuses on scenarios of fragmentation, trajectory, and impact energy in regions near our planet. To understand an extreme scenario realistically, let us imagine that an interstellar object the size of 3I Atlas, fragmented or deflected, were on a collision course with Earth. The analysis begins with the impact energy calculated using the formula for kinetic energy: 1/2 mass times velocity squared. At speeds greater than 50 or 60 kilometers per second, even bodies of about 100 meters can release energy equivalent to millions of tons of TNT. Objects larger than 1 or 2 kilometers could trigger catastrophic regional effects and temporarily alter the climate. But it must be insisted, this is not what will happen with 3I Atlas, but what scientists study to be prepared for any other with similar characteristics in the future. In the history of our planet there have been numerous impacts, some minor, others devastating. The Barringer crater in Arizona is proof that an object of about 50 meters can generate a notable impact. Tunguska demonstrated that even without a direct impact, an explosion in the atmosphere can destroy thousands of square kilometers of forest. Chicxulub demonstrated that objects several kilometers in size can change the history of life. What differentiates our time from the past is the capacity to detect, calculate, and react. It is not about avoiding every impact, but about avoiding being taken by surprise. The current monitoring of 3 Atlas allows us to know that its minimum distance to Earth does not represent a risk, but its passage serves to test prediction systems. Telescopes like Pan-STARRS, Atlas, the Catalina Sky Survey, and the NEOWISE satellite follow its trajectory. Constant tracking confirms what is already known. It will not deviate towards our planet. However, every image captured, every variation in its brightness, and every correction in its orbit contributes to improving the algorithms that will be used for future objects, especially those that could represent a threat. The real scientific concern does not arise from 3I Atlas, but from the undiscovered objects. There are millions of small bodies in the inner and outer solar system, and it is estimated that we only know a fraction of them. Current telescopes detect the majority of objects larger than 1 kilometer, but many smaller ones, the size of a building, could go unnoticed until shortly before they approach. Not because science does not want to see them, but because they are dark, reflect little light, and only become visible when they are already close. Therefore, although this interstellar object is not dangerous, its study justifies investments in more powerful telescopes and more advanced automated systems. An example is the Vera C. Rubin Observatory under construction in Chile. This telescope will take repeated images of the sky every few nights, identifying any moving object with unprecedented precision. Its goal is to track asteroids, comets, interstellar objects, and any body that could represent a risk. The future of planetary defense depends on this type of technology, not on assumptions or rumors. Knowing what is out there is the first step to protecting what is here. From a geological point of view, Earth has faced impacts long before humans existed and will continue to face them on very long time scales. The difference is that now, for the first time in history, there is the possibility of detecting and perhaps avoiding some of them. That does not mean that every danger is eliminated, but that knowledge reduces uncertainty. Science does not promise that nothing will happen, but it offers tools to understand what can happen, when, and with what consequences. That is the reason why scenarios like the worst possible one are not fantasy, but exercises in preparation. 3I Atlas is, in this context, a reminder that we are not completely alone in space, but neither are we defenseless. It did not come to destroy or alter the sun, nor to threaten life. It came to teach us how to observe better, how to calculate better, how to respond more quickly, and how to communicate responsibly. While some use its name to generate fear, science uses it to generate knowledge, and that knowledge may one day make the difference between vulnerability and survival. When speaking of extreme scenarios related to interstellar objects like 3I Atlas, a common concern arises. If the current risk is practically zero, why worry or even consider a worst-case scenario? The answer is simple and completely scientific. Because prevention is not based on what is happening, but on what could happen if conditions changed even slightly. And the only way to prepare for the improbable is to understand it before it happens. It is not about fear but about responsibility based on knowledge. Humanity has not always had this capacity for anticipation. For almost all of its existence, astronomical phenomena were interpreted as divine signals or inevitable events. Orbits could not be calculated nor eclipses predicted with accuracy. Today, in contrast, every object like 3I Atlas can be tracked, modeled, and analyzed with a vision that spans years into the past and the future. That advantage does not eliminate risk completely, but it reduces uncertainty. And in science, reducing uncertainty means saving lives even if a catastrophe never occurs. Earth revolves around the sun on a trajectory that seems stable, but that equilibrium depends on extraordinarily precise factors. The distance to the sun allows for the existence of liquid water. The atmosphere filters ultraviolet rays and maintains a temperature compatible with life. The magnetic field deflects charged particles from the solar wind. The moon stabilizes the planet's axis of rotation, preventing abrupt changes in the global climate. All these elements allow life to exist and develop. However, it also means that a large alteration provoked by a cosmic impact could modify that equilibrium. Not necessarily eliminate life, but transform the environment irreversibly, as has happened before. Geological evidence confirms that impacts of great magnitude have happened repeatedly. The Chicxulub event was not the only one. In South Africa, there is the Vredefort crater, possibly the largest on the planet, caused by an object between 10 and 15 kilometers in size over 2 billion years ago. In Canada, there is the Sudbury Basin, also the product of a gigantic impact. These events occurred long before humans. Earth continued to exist, but the world was never the same again. What science seeks today is not to stop nature, but to understand it sufficiently so as not to be surprised. 3I Atlas has none of the characteristics to be a real threat. Neither its trajectory, nor its mass, nor its speed point towards Earth. It does not have an orbit that intercepts ours. It does not pass close enough to giant planets to suffer significant deviations, and it shows no signs of massive fragmentation. However, the study of its passage allows for the evaluation of how quickly we could detect changes if it were to do so. Automated systems can identify minimal deviations in its orbit, and telescopes can detect variations in its brightness indicating the shedding of material. That is the true value of following it so closely, not for what it can cause, but for what it can teach us. Planetary defense is based on several levels. The first is early detection. The second, trajectory analysis. The third, risk assessment. The fourth, action if necessary. But there is an additional level that is seldom mentioned: education. Informing the public correctly is essential. If communicated with fear or exaggeration, credibility is lost. If minimized or ignored, an opportunity for preparation is lost. Science must explain clearly, there is no risk with 3I Atlas, but natural risks exist in the universe, and knowing about them is part of protecting life. Something that makes interstellar objects special is how little we know about them. Unlike comets from the solar system, whose behavior has been studied for centuries, these visitors come from completely different environments. Perhaps they formed around different stars with different chemical compositions under temperatures and pressures that do not exist here. Studying them is like receiving a fragment from a distant place without sending a spacecraft. And although 3I Atlas will not pass close enough to be reached by a mission, its observation from Earth allows us to obtain information about its speed, brightness, and surface composition. Every photograph, every light spectrum is a window into another stellar system. With technological advances like the James Webb Space Telescope, it is now possible to analyze the infrared light of small objects with greater precision than before. Webb has detected molecules on exoplanets, atmospheres on distant worlds, and details in distant galaxies. If it can be pointed towards an object like 3I Atlas at the right moment, It could reveal if it contains organic compounds, water ice, carbon monoxide, or other elements. That information is crucial because if one day an interstellar object represented danger, knowing its composition would help decide whether it is better to deflect it, fragment it, or simply monitor it until its passage. In an extreme but scientifically possible scenario, an interstellar object could pass close enough to Jupiter to be temporarily captured and end up orbiting the Sun. If that occurred, over time it could cross Earth's trajectory. This is not the case for 3I Atlas, but it has happened with comets like Shoemaker-Levy 9, which was captured by Jupiter and ended up impacting the planet in 1994. The explosions were visible from Earth and released energy equivalent to millions of atomic bombs. Although that event had no consequences for us, it demonstrated what can occur when an object falls under the influence of a giant planet. Therefore, although no danger exists today, studying these phenomena moves us away from improvisation. Science does not say that everything will always be fine. It says something more honest. The universe is dynamic, sometimes violent, and the only way to protect ourselves is to know it. The unknown is not combated with fear but with data. As humanity advances technologically, the way we understand and face cosmic risks also changes. What was once seen as inevitable destiny can now be analyzed, prevented, or at least anticipated. Objects like 3I Atlas, although they do not represent a threat, remind us how fragile and at the same time how resilient our planet is. Fragile because it depends on very precise conditions to maintain life. Resilient because it has survived impacts, ice ages, mass extinctions, and tectonic changes for billions of years. Scientific knowledge allows these two realities to coexist. Knowing that we are vulnerable but also capable of understanding, acting, and protecting. Sky surveillance is not an improvised task nor limited to a few people. Every night, telescopes all over the world capture images of specific regions of space and compare what they see with previous records. If a new point of light appears or if a known one changes position, it is analyzed. That is how 3I Atlas was detected. A sequence of photographs showed that it was not moving like a typical asteroid or a common comet. Its speed and direction indicated that it came from outside the solar system. Those initial data were later confirmed with additional observations and orbital calculations. This procedure is routine, but every discovery like this remains extraordinary. After confirming it as an interstellar object, astronomers began to project its route. Knowing where it is going is not enough. One must know which celestial bodies will be near it, how they could influence it, and if any of them could alter its trajectory. Current orbital models even include the gravitational effect of dwarf planets, large asteroids, and even the pressure exerted by sunlight on the object's surface. It is a way to ensure the margin of error is minimal. Today, thanks to these tools, it is known that 3 Atlas will not cross Earth's path nor that of any planet in a dangerous way. If an interstellar object were ever to deviate unexpectedly, it would not be by absolute chance. There would have to be a physical reason. The gravity of a giant planet, a collision with another body, fragmentation from extreme heat, or excessively rapid rotation. Astronomers contemplate these factors. For example, when an object spins at a very high speed, its internal parts experience tensions that can cause it to disintegrate. If 3 Atlas had a fragile structure and accelerated rotation, it could fracture, but so far there is no evidence that this is occurring. Its brightness has not shown sudden decreases nor gas explosions, typical signs of bodies breaking apart. Everything indicates it will remain intact during its passage through the solar system. Thinking about the worst-case scenario serves to evaluate human preparedness in the face of the unexpected. If an object on an impact trajectory were discovered heading towards Earth today, every minute would count. And although it may sound alarming, the most important thing is that there would be time to act if it is detected with anticipation. Warning time is the most valuable resource. If there are years, it can be deflected. If there are months, it can be studied and planned for. If there are days, an evacuation can be carried out. If it is detected only seconds before, as happens with many meteors, there is barely time to observe and record. That is why, although 3I Atlas does not represent a threat, its early detection demonstrates that the surveillance system works. International cooperation is fundamental in this entire process. No single country can monitor the entire sky by itself. Observatories in Europe, America, Asia, and Oceania share data through astronomical networks, and when a potentially hazardous object is identified, a global protocol is activated. The information is transmitted to centers like the MPC, NASA's JPL, and ESA. Even countries without space agencies participate through universities, laboratories, or tracking stations. That network of collaboration turns the entire planet into a collective observatory, and that is one of humanity's greatest strengths in the face of the universe. Life on Earth exists thanks to a delicate balance, but also to natural mechanisms that protect us. The atmosphere causes most small bodies to disintegrate before touching the ground. The magnetic field deflects solar particles that could destroy molecules essential for life. Jupiter acts as a gravitational shield, attracting or deflecting comets that might otherwise come too close. The Moon stabilizes Earth's axis. All these factors work together to maintain stability, but none of them is invincible.